This next video on complex analysis. In this video, we will look at the polar representation of complex numbers. So we have this polar coordinates. We have these polar coordinates r and theta, which represents a complex number z, right? So let us see how we define these these parameters r and theta. So basically, we have a complex number z, right? And we know that we can represent that complex number in the Cartesian plane, right? So we have a point a comma b. If your complex number is a plus iota b, then we know that we have a representation of that complex number in the Cartesian plane as the point a comma b, right? And then we can define this distance of that point from origin as r, right? This is actually equal to modulus of z. This we defined in the last video. So this is positive square root of a square plus b square, right? This is how we define this parameter r. So this parameter r is the distance of the point representing your complex number in the Cartesian plane from the origin, right? So it is clear that this is always a positive quantity. So we have this r greater than equal to 0, right? And r is actually modulus of z. So it is pretty simple to define this parameter r. It is little bit difficult to define this parameter theta. So let us see how we can define this parameter theta. Okay. So how do we define this parameter theta? We have this theta we define as we have a complex number z, represent it as a point in the complex this complex plane or Cartesian plane or Argand plane, whatever you want to call it. Then have this vector which we had seen, that every complex number can be represented by the vector which joins the origin to the point which represents the complex number. So you have this vector. Now measure the angle which this vector makes with the positive real axis. This is your positive real axis, okay? And this angle, if you are measuring in counterclockwise direction, then you have to treat it as a positive angle. And if you are measuring it in the in the clockwise direction, not anti-clockwise, in the clockwise direction, if you are measuring, your angle will be negative. So basically, theta is the angle of inclination of a vector z measured positively in the counterclockwise sense from the positive real axis. Okay. For example, if you are in the first quadrant, okay, then this angle, and suppose you want to measure in the counterclockwise direction only, so you want your theta to be positive, right? Then this will be your angle. This is your a plus iota b. This is a vector, right, which represents your point. So you have this angle theta, and obviously you can what will be this angle theta? You have this length as a and this length as b, because a and b both are positive because you are in the first quadrant, right? So you can use this tan theta will be equal to b upon a, right? So your theta will be tan inverse of b upon a when you are in the first quadrant and you want your angle to be positive, right? And suppose you are in the second quadrant. If you are in the second quadrant, your a will be negative and b will be positive because you are in the upper half plane but on the negative side of real axis. So this length still is mod of a and this length is still mod of b. So basically, if you take the absolute values of a and b, they are positive. So they will represent the lengths of the triangle. So now you consider this triangle. In this triangle, tan phi will be modulus of b upon a. But you want this angle theta. This angle theta is actually pi minus phi. And phi is tan inverse of modulus of b upon a. So you have this as your phi. And so your theta will be pi minus tan inverse of modulus of b upon a, right? And suppose you are in the third quadrant and you want to measure this angle, right? Okay, you want to have a positive angle, so you want this to measure this angle. So again, in this case, a plus iota b, both a and b are negative because you are in the third quadrant. But again, the modulus will represent this length and modulus of a will represent this length. So you have tan phi is equal to tan phi is equal to mod of b upon mod of a. So you have phi is equal to tan inverse b upon a. Now you can see what is your angle theta. Your angle theta is this angle pi plus phi. So you have theta is equal to pi plus tan inverse of b upon a, right? And similarly, you can have your complex number in the fourth quadrant. Again, this length will be your modulus of b and this length will be your modulus of a, and your phi will be tan inverse of modulus of b upon a, and your angle required is you need this angle, right? So this is basically 2 pi whole angle minus phi. So your theta will be 2 pi minus tan inverse of modulus of b upon a. So this is how you can compute your angle theta, right? Now, okay, there is one problem. Okay, maybe I will explain that in the next slide. Okay. Okay, what is that problem? That problem is, suppose I am here, right? And this is my theta, right? This angle is theta, right? And now you move all around. So you cover 2 pi and then again you came here, right? So this is also 2 pi plus theta, right? Again you go 2 rounds and again come back. So this angle can also be 4 pi plus theta and so on. So basically, if theta, which I measure as the angle, and I will call it as the argument of z, theta, which we measure in the last slide, we will call it as argument of our complex number, right? If theta is an argument, then theta plus 2 pi is also an argument, theta plus 4 pi is also an argument, theta plus 6 pi is also an argument, and similarly theta minus 2 pi, theta minus 4 pi, and so on, right? So basically, if theta is an argument of a complex number z, then theta plus 2k pi, where k is an integer, right? All these quantities are the argument for your complex number z, right? For example, if I have this number z plus iota, what will be the argument for this number? We have this z is 1 plus iota, so we are in the first quadrant, so we have this one length here and one here, so this is our theta, right? So theta will be tan inverse of 1 upon 1, so that is pi by 4. So I can represent this point 1 plus iota, so this is my pi by 4, 45 degrees, right? But again I can go make one round and again come back, so it is also pi by 4 plus 2 pi and so on, right? So for this particular complex number 1 plus iota, I know that these are the possible values of my argument of z. Okay, so basically the theta which we are looking for. So these are the possible values for my theta. So they are infinite in numbers, right? For this particular complex number 1 plus iota, r is fixed. R is 1 square plus 1 square. So this is square root of 2. So I need two parameters, r and theta. R is fixed, but theta can take infinitely many values. So I have to do something about that. Okay. So it is very clear that if you fix that I want my theta such that it should be in the interval 0 to 2 pi, or in the interval 2 pi to 4 pi, okay, or in the interval minus pi to pi. So any interval of length 2 pi, okay, for any interval of length 2 pi, every point will have exactly 1 theta, right? So what we have to do, we have to restrict our interval, right, where you want your angle to lie, right? So basically our job is to fix an interval of length 2 pi such that theta belongs to that interval, right? That is what we have to do, okay, right? If we do so, if we can do like this, then theta for every point theta will be unique. Right now what is happening, for this particular point I have infinite number of thetas available. For this particular point, I have infinite number of thetas available, but I want my theta to be unique at every point, right? For that, I have to fix an interval of length 2 pi, right, where theta should lie. Let us see how we can do that. So let us fix our interval as minus pi to pi, okay, with minus pi open and pi closed, right? This is an interval of length 2 pi, right? Okay, right? If we have this interval, so whenever we have this point in the first quadrant, then we have to measure it like this. If we have a point in the second quadrant, we have to measure like this, okay, like this I have shown here. And if we have a point in the third quadrant, we will not go like this, because that way we are going out of this interval, because that angle will be more than pi, but we will go like this, okay, that angle will be in this interval, right? And if we have a point in the fourth quadrant, we will go like this. So basically what you have to do for points in this plane, okay, you have to go like this clockwise, and for points here you have to go anti-clockwise. And for this particular line, if you go like this, it will have argument pi, and if you go like this, it will have argument minus pi, but minus pi is not included in our interval, so we have to go counterclockwise. So basically what we have to do for points here, Okay, including this line, we have to go counterclockwise, and for points here we have to go clockwise, right? Okay, so if we do like this, what will be the argument in each quadrant? Here in the first quadrant we have this a plus iota b, so you have your theta as tan inverse of b upon a, right? In the second quadrant, if you compute this tan inverse of b upon a, you will get this angle theta phi, but you want this angle theta, so your theta will be pi minus tan inverse of b upon a. This is important to remember. Okay, and here in the third quadrant, see, in the third quadrant what you will have, I will draw it here maybe. Okay, in the third quadrant you have this, and you want to measure like this, right? But when you compute this, this will give you tan inverse of b upon a, right? But you want this angle, so how you can compute this angle? This angle is pi minus, this angle is pi minus tan inverse b upon a, right? But then you have to put a negative sign because you are measuring it clockwise, so it will be minus pi minus tan inverse of b upon a, right? And if you are in the fourth quadrant, then this angle you are measuring, right? This will be your tan inverse of b upon a, but you have to put a negative sign because you are measuring it in the clockwise direction. So this is how, if we will restrict our interval where theta can lie, then for every point theta is uniquely defined, right? That is what we want, right? And this particular, fixing this particular theta, right? This theta was argument of z. So basically this is a function, argument of z is a function from set of complex numbers to if we fix an interval, it will be initially it was just r, but it was not a function because for a particular z I had so many values, right? So that doesn't satisfy the definition of the function we know, right? So we fixed it this way, that we don't want it from c to r, we want it from c to some particular interval of length 2 pi, for example say minus pi to pi, right? But it can be any interval, right? And this is a function, right? And when you fix the interval, this is well defined function, right? So it means that every complex number has unique argument of z, and when this interval is fixed minus pi to pi, you can also fix 0 to 2 pi, right? And 0 to 2 pi or minus 2 pi to 0, it's up to you. You can fix any interval of length 2 pi, right? But when you fix this particular interval, then you have a special name for your argument of z. You call it as principal argument of z, and you denote it with capital A. Okay, so when your theta is such that it belongs to the interval minus pi to pi, you call it as principal argument of z and denote it with capital A, ARG you write it, right? Okay, so already I told you that there is nothing particular about this interval. You can choose any interval of length 2 pi. For example, if I want to, already we have seen that if we choose an interval from minus pi to pi, then your angles will look like this. From here it will be 0 to pi, and from here it will be 0 to minus pi, right? And these points will be having angle minus pi plus epsilon, where epsilon is very small, and these points here near the negative real axis, but upsides will have points of the angles of the form pi minus epsilon, where epsilon is a small number, right? And you can choose the interval 0 to 2 pi also, and you can note that here your function argument of z, which is actually capital argument here in this case, in this interval, is discontinuous at this line, because from above the value is approaching pi and from below the value is approaching minus pi. So we have a discontinuity for this particular function argument of z at the negative real axis, right? And here if you take the interval 0 to 2 pi, you want all the argument of z should lie in 0 to 2 pi. So it means that you want 2 pi is closed and 0 is open. So all the points on this line will have their value of argument as 2 pi. Then you go like this. You start from 0 plus epsilon 2 and so on, so on, so on. And when you come back here again, right? So you have the values of the function as, for example, here you will have 2 pi minus epsilon, right? But here you have 0 plus epsilon. So you have a jump of 2 pi. Right? You have a jump of 2 pi. So again your function is discontinuous. This time it is discontinuous on positive real axis. Okay. So Similarly, you can have an interval like 2 pi to 4 pi. Again, you have a jump at this real axis, positive real axis. Okay, right? So in fact, you can have something like this. You can start from any complex number z0 and you can reach up to z0 plus 2 pi. So it's the only thing, not complex number, I'm sorry, any real number. For example, I start with pi by 3 to pi by 3 plus 2 pi. This will also define one branch of argument of z, right? And in this case, you will start from pi by 3. Pi by 3 is 60 degrees. You will start from here and you will move like this, right? And in this case, your function will be discontinuous at this particular line, theta is equal to pi by 3. For example, in this case, it was discontinuous at theta is equal to minus pi. In this case, it was discontinuous at theta is equal to 0. In this case, it was discontinuous at theta is equal to 2 pi. So in this case, it will be discontinuous at theta is equal to pi by 3, right? So this is, and this is like this particular line is called branch cut, that I have explained in the next slide. So what I want to conclude here is that you can have argument of z and you can fix any starting point. For example, here I fix minus pi, here I fix 0, here I fix 2 pi. So I will denote it as argument z and here I will write that fixed point minus pi. Argument of z, here it is 0. Argument of z here at 2 pi. So in general, I can have any argument of z, z not specified. This is one branch of my argument of z, right? So basically what we are doing is, we have so many ways to fix our theta and I can choose any one way, okay, out of those so many ways, okay, and that will define my one branch of argument of z. And in particular, this is most useful branch, right? We will call it as principal argument and we denote it with arg z. So basically this is the most useful thing for us. We will keep, I think we will use this again and again, okay. Okay, so let us see what was branch cut. So basically we have seen that when we fix this angle between minus pi to pi, then we have a jump of 2 pi when we move from this axis from minus pi to pi. So here when I am computing the angles, I am getting pi. This side I am getting minus pi. So my function is discontinuous at this line and this line is called branch cut. Branch cut for which branch? For this branch. Okay. And in this case, when I fix the angle from 0 to 2 pi, again this is my branch cut because this side angle is 0 and this side angle is approaching 2 pi. So this is called branch cut of which branch? Argument of z with 0 as my fixed point. And again, when we are having this interval, then the angles when we are approaching from this side is 2 pi and the angle from this side is 4 pi. So I have a jump of 2 pi. So this is my branch cut. Okay, for which branch? For argument of z with 2 pi fixed. In general, theta is equal to z naught is your branch cut for the branch argument of z with z naught fixed. Okay. So this is how we will define our theta. Okay. So let us do one problem. Okay. And one more thing I want to like specify. Obviously, argument of 0. We don't know what is the argument of this point. Actually, we don't need this also because basically what we are doing, we are like denoting every point with r and theta, right? Okay. So such that your z is okay. How we can write if we have a z and we have r and theta, then what is the relation between r, theta and z? So basically you have z is equal to a plus iota b. So a is basically your, this is your a, this is your r. So your a is actually r cos theta and b is your r sin theta, right? So you have a as r cos theta, b as r sin theta, right? So your z is r cos theta plus iota sin theta. So your r is z is r e raised to power iota theta, right? So this is the polar form of the complex numbers, right? And when you have z is equal to 0, this is your point you are representing. Your r is 0. So your polar form r e raised to power iota theta is 0 into e raised to power iota theta. So we actually don't need theta, right? So, and also we cannot sensibly define what this will be for any branch. So we don't define argument of 0, right? And actually we don't need that, right? Okay. Now write the polar form of this particular complex number, right? For we know that if we want to write the polar form, we need two parameters r and theta. So first let us compute r. R will be a square plus b square square root. So 1 square plus square root of 3 square, that will be square root of 1 plus 3, that is square root of 4, that is 2, right? Now we are in the first quadrant, right? Your theta will be b upon a tan inverse. So you have theta is equal to tan inverse of b upon a, that will be pi by 3. So but we know that if the pi by 3 is an argument, then pi by 3 plus 2k pi, where k is an integer, will be argument. But if we want to stick to the principal argument, then it will be pi by 3. So our polar form is 2 into cos of pi by 3 plus iota sine of pi by 3. You can write it as 2 e raised to iota pi by 3. This is the polar form of this particular complex number, and it is very useful. We will see this. Okay. Thank you so much.